Imagine gazing through a vast, dark expanse, miles beyond our blue planet and feeling the enormity of time and space. Now, picture this: the light from ancient galaxies, billions of years old, is traveling through that darkness, reaching our eyes for the very first time. This light is a glimmer from the distant cosmos, carrying with it secrets from the universe's earliest epochs. As we embark on this extraordinary journey into the depths of space, we're not just searching for spectacular views of twinkling stars, we're unearthing the foundational stories of our universe. What lies behind the veil of these ancient galaxies? You might be wondering, how do we even know they exist, and what do they tell us about the very nature of reality? Stick with us. In the next few minutes, we're going to unlock the incredible mysteries of the oldest known galaxies in the universe. You'll discover not just fascinating facts, but also the profound implications these ancient worlds have for our understanding of the cosmos. So settle in, grab your favorite snack, and prepare to have your mind expanded as we explore the elusive edges of the universe and our understanding of time itself. What if I told you that some of the oldest galaxies we've discovered date back to a time just a few 100 million years after the Big Bang? They give us a near-pristine glimpse into the universe's formative years, the days when stars and galaxies first coalesced from the smoky clouds of primordial gas. The earliest light we observe helps paint a picture of cosmic architecture that has shaped the very fabric of existence. These fascinating bastions of history not only exhibit the evolution of galaxies but also tell us about the forces that shaped their birth and growth. To better grasp the significance of these ancient clusters, let's dive into a few remarkable examples. Meet the galaxy known as GN-z11, a name that might sound cryptic but represents the frontier of astronomical discovery. Found nearly 13.4 billion light-years away, GN-z11 is a living relic of the universe's infancy. Consider this: we see it as it was just 400 million years after the Big Bang. This means the light we perceive today left the galaxy when our universe was only about 3% of its current age. Fascinating, right? It's almost like flipping through a photo album of antiquity, with each snapshot revealing details of formative cosmic events. You may be wondering, what makes this discovery so groundbreaking? Well, GN-z11 challenges our understanding of galaxy formation. This galaxy is remarkably massive and seems to be producing stars at an astonishing rate. In fact, it's forming stars at a speed 10 times greater than our own Milky Way today. This raises intriguing questions about how such galaxies could exist so early in the universe's life. Did they form directly from the material left over from the Big Bang, or did they face other cosmic players that helped accelerate their growth? It's moments like these that prompt scientists to reevaluate everything we think we know. Let's not stop there. Another striking discovery is the galaxy EGS-CS8-1, which dates back to about 10.5 billion years ago. At this time, the universe was experiencing its cosmic noon, a period where star formation peaked. EGS-CS8-1 is remarkable for housing more stars than we once thought possible during that era. The sheer scale of star-forming activity begs tantalizing questions about how galaxies evolved through epochs filled with violent interactions between dark matter and intergalactic gas, shaping and reshaping the universe. But what if some of these ancient galaxies hold within them answers to the very essence of life's building blocks? You heard me right. One of the most fundamental pursuits in astrophysics is understanding the conditions required for life. As astronomers peer into deep space, searching for ancient galaxies, they're not just looking for distant points of light, they're seeking clues about the chemical diversity that led to planets and, ultimately, life itself. Speaking of life, the existence of galaxies like A2744_YD4, located within a cluster formed roughly 4 billion years after the Big Bang, brings more to the table. This peculiar galaxy holds profound insight into the era's chemical enrichment. After a series of supernovae, the materials released contributed gases essential for the formation of stars, and potentially for life. The intricate dance of elemental dispersal and gravitational dynamics inside these galaxies continues to mess with our expectations about how quickly and efficiently the universe creates the components necessary for life. It's an enthralling push and pull of forces with cosmic implications. So, with all this fascinating backdrop, you might think, is there a limit to how far back we can see? This leads us to the very cutting edge of our technological capabilities. Telescopes like the Hubble Space Telescope and the newly launched James Webb Space Telescope are our key allies in this quest. Why? Because they are equipped to observe these precious light echoes from antiquity. The Hubble, with its unmatched ability to peer into deep space, has given us blueprints from the very farthest reaches of our galaxy. But it's the James Webb Space Telescope that holds the promise for unveiling the universe's most enigmatic secrets. With its advanced infrared capabilities, Webb can capture light from the very earliest stars and galaxies, weaving an even more detailed tapestry of cosmic history. What comes next will leave you speechless. We are on the brink of revelations that may redefine our understanding of cosmic evolution. Incredible insights may soon be uncovered regarding the rapid formation of galaxies and their explosive early growth. Could it be possible that we underestimated how quickly the universe began to evolve? Let's take a moment to think about the concept of viewership in astronomy. When we look at these ancient galaxies, we aren't just seeing relics of the past, but instead, we are engaging in a profound conversation about the future of the universe itself. Every galaxy holds a story, stories that might help us understand not just how galaxies evolve, but how we, as a species, relate to our universe. Now, here's something you probably didn't expect. Not all ancient galaxies we discover are simply larger and more luminous. Some defy categorization, existing in awkward states of bizarre transitions. Take, for instance, the peculiar galaxy ID 14129 plus 3001. This distant universe provides a fantastic case study of a galaxy caught in the throes of rapid evolution. It exhibits characteristics of both mature galaxies and younger, more active star-forming types. This duality raises essential questions. Is it possible that these galaxies are hybrids, balancing on the edge of instability? Are they mere glimpses into the transformative dance that characterizes galaxies nearing the end of their lifespan? Amidst these wonders and revelations, allow me to pose a thought-provoking inquiry. What if our very galaxy, the Milky Way, is on a journey towards becoming one of those ancient and intricate structures that we are now just beginning to fully comprehend? As we unravel these cosmic narratives, we might also find ourselves tracing the potential paths of our own galaxy's evolution. And speaking of evolution, it's essential to connect the dots among these ages-old galaxies and our own origins. The curiosity doesn't stop at the how, but journeys deep into the why. What motivates the universe to create such strikingly diverse galaxies? The fabric of space and time is interwoven with influences that destabilize, mutate, and transform these celestial bodies, all pointing to a grander design that shapes them into what they will ultimately become. Now I want to take you back to a concept you might have pondered: time itself. Viewing these galaxies is like peering into the face of time. We are witnessing snapshots from epochs long gone. But what exactly does this teach us about time? Some physicists propose that observing ancient galaxies can help us understand dark energy, the mysterious force driving the acceleration of the universe. Could it be that these earliest galaxies, dating back to a time when the universe was expanding rapidly, were subjected to different physical laws that could unravel new theories on time as a fundamental construct? Answers lay in waiting among the shimmering light of these distant cosmic jewels. As we continue to explore, we will uncover even more sophisticated models that predict the different interactions of galaxies and their surroundings. Are you ready to redefine everything you thought you knew about the cosmos? But fear not, this journey doesn't end here. We've only just begun to scratch the surface of the incredible stories told by these distant galaxies. In our next segment, we'll delve into their intricate structures, the gravitational forces at play, and what future explorations are likely to reveal. What ancient secrets remain hidden in the cosmic mists awaiting their turn in the spotlight? Join me as we leap into the next chapter of our exploration into the universe's oldest and most mysterious inhabitants. As we continue to unravel the mysteries held within the depths of these ancient galaxies, we must turn our focus toward their structures. Each galaxy is like a unique work of art, painted by the forces of gravity and time. Understanding how they are formed, how they interact, and how they evolve is crucial for piecing together the grand puzzle of cosmic history. Consider the role of gravitational interactions among galaxies. These forces don't just dictate shape and size, they're fundamental in determining a galaxy's fate. Galaxies can collide and merge, leading to spectacular cosmic fireworks and often resulting in the creation of new stars. Such gravitational dance proves that galaxies aren't isolated islands in a vast ocean of space, they are interconnected, sharing matter, energy, and history. Observing these colossal collisions in ancient galaxies leads us to appreciate how heavily intertwined these formations are even billions of years ago. To illustrate this, let's discuss the phenomenon of galaxy mergers, which were exceptionally common in the early universe. One of the most captivating examples is the merger of two massive galaxies in the early epochs, which may have fueled bursts of star formation. The aftermath of such collisions often yields a complex tapestry of new star creation amid the debris of galactic material. As we look at these ancient celestial giants, astronomers can track this intricate process back through time, observing the fingerprints of past interactions. The evidence of these stellar forges can illuminate our understanding of the dynamism at play in the early universe, raising questions about how long those interactions remained active and what impact had on each galaxy's subsequent evolution. These ancient siblings often showcase structures and phenomena that challenge our existing models of galaxy formation. Our findings suggest that some of these early galaxies had significantly clumpy distributions of stars and gas. The traditional view posited that galaxies formed from smooth, uniform distributions of matter. Yet, the observations we make confirm that many of these distant galaxies exhibited irregularities that suggest turbulence and complex dynamics were at play. This vital evidence nudges us to consider alternate scenarios, indicating that the formation of galaxies may have followed more chaotic paths than we once assumed. As we probe deeper into the structures of these ancient worlds, we come across another enigmatic facet, the dark matter halo. Dark matter, an invisible form of matter that doesn't emit, absorb, or reflect light, is crucial for galaxy formation. It envelopes galaxies, acting like a cosmic scaffold that constrains the visible elements. By studying the distribution of stars and gas in some of the oldest galaxies, scientists can infer the presence of dark matter and its influence on galactic evolution. This leads us to a significant question: how much dark matter was present when these galaxies first began to form? Could this missing piece of the cosmic puzzle hold the key to understanding the different formation pathways of early galaxies? Speaking of data and discoveries, we must highlight the impressive advances in technology that allow us to push the boundaries of our understanding. The capabilities of the James Webb Space Telescope represent a monumental leap in gathering data on ancient galaxies. Not only does it pierce the veil of cosmic dust obscuring older galaxies, but it also opens our eyes to their spectral signatures, revealing the abundance of elements like carbon, oxygen, and nitrogen. These elemental fingerprintings serve as critical indicators of the chemical processes that occurred within these galaxies and how they have evolved. As Webb captures faint remnants of starlight from these galaxies, it provides crucial information about the birth and death cycles of stars. Each supernova explosion not only marks the end of a star's life but also plays a monumental role in seeding the galaxy with heavier elements essential for creating the next generation of stars and planets. The intricate chemistry born from these stellar nurseries finally ties back to our interest in planetary formation and the nurturing of life in the universe. What we may witness is not just the remnants of historical processes, but clues that could lead us toward understanding how life as we know it may have come to be. Now, let's not overlook the role of cosmic feedback, a process that occurs when explosive stellar activity impacts galaxy evolution. Supernovae and the intense radiation emitted during periods of star formation pump energy back into the surrounding intergalactic medium. This can trigger further star formation, while also expelling large amounts of gas from the galaxy, restructuring its very nature. Understanding this continuum of stellar feedback allows us to view galaxies not as static entities but as dynamic systems continuously emerging from the chaos of creation and destruction. What we learn from these narratives affects our views of not just ancient galaxies but also their descendants, potentially offering insights into the future of our own Milky Way. While we examine the life cycles of stars within these ancient galaxies, we start to see fascinating patterns emerge. Stellar populations.